This talk is a collaboration with Tiomir Asparohov, my Mplus colleague. It builds on a series of our recent papers on both short and long longitudinal data, as well as 2 recorded web talks and a forthcoming web talk, which are posted on the Mplus website. And we want to thank several researchers who've been generous enough to share some of their data with us, and which we have used to illustrate the methods we have worked on. Here's the outline. I'll start with some motivating examples from 3 different data sets having to do with measurements of stress, alcohol consumption, suicidal ideation, substance abuse, and negative affect. And the sample sizes range from about 300 to 1,300 individuals. In part 1 then, I focused on short longitudinal data, often called panel data, where the number of time points are typically in the order of 3 to 10. First, I give a brief refresher of longitudinal modeling with continuous outcomes in the form of dynamic models as well as models with autoregressive residuals. And then I turn to categorical outcomes, which is the main topic. I'll give you a brief introduction to multivariate modeling with categorical outcomes, particularly the multivariate probit model. I'll talk about the statistical specification of the model, mention the identification issues, and talk about estimation. Then I'll turn to model testing. Section 4, then, we have our first applications of these binary RI-AR models. So binary outcomes and random intercept autoregressive models that we'll go through in the form of suicidal ideation and abstinence in the alcohol study. In section 5, we switch from the binary case to the polytomous case and look at ordered categorical, that is ordinal outcomes. And we'll also discuss a new type of model that we call 2-part ordinal. And we're going to look at the model specification and use the example of a 5-category alcohol risk variable. I'm going to take a look at a randomized trial and the treatment effects, where we compare regular ordinal modeling and 2-part ordinal modeling in terms of the effects. In section 6, we come to the analysis of 2 processes and look at the cross-lag panel modeling with categorical outcomes. And as an example, we can look at the cross-lag effects between a continuous variable, the stress outcome, and a 5-category ordinal alcohol risk outcome. And then finally, in part 2, we turn to longitudinal data, that is intensive longitudinal data, characterized by many time points, say 50 to 100, and also very frequent observations close in time. In section 7, then, I'll talk about 2-level time series analysis that we call DSEM in the Mplus context, dynamic structural equation modeling. We'll talk about 2-level cross-lag modeling of positive and negative affect, and 2-level 2-part analysis of negative affect, daily cycles of positive affect, and interactions in a randomized trial. So let's turn to motivating examples then from the 3 data sets. So on slide 5, a key data set is from the combined study of alcohol use disorders. So that's a 16-week multi-site randomized double-blind clinical trial comparing various treatments of alcohol, behavioral treatments, and medication. And that's from a classic article in Journal of the American Medical Association. So sample size is a little bit over 1,000, and we have baseline measures before the intervention, and then weekly observations up to week 16 and a week 52 follow-up. We're going to focus on 2 variables, alcohol risk and stress. So alcohol risk is a 5-category variable: abstinence, low risk, medium risk, high risk, very high risk, where the risk levels are based on the amount of alcohol consumed. The stress variable is a brief version of the perceived stress scale, and there's been an interest in studying the interplay between alcohol problems and stress. For instance, in this article, Stress and Alcohol Use Disorder, where it was found that stress causes drinking. So an interaction between these two variables in a certain direction. This dataset also has several covariates. We're going to focus on the intervention covariates. There are 9 groups corresponding to medication, placebo, and therapy, plus other covariates. The stress variable looks like this. It's a 4-item version of this stress scale with scores between 0 and 16. Has been used in this article in Journal of Studies of Alcohol and Drugs. And I would say one can treat this as a continuous variable, although it's not perfectly normal. We can use non-normality robust maximum likelihood. The percentage at the lowest score of 0 increases with time, but does not exceed 15%. And when you don't have a strong floor effect, I would find it appropriate to use continuous variable linear modeling techniques. Now for the key variable, the alcohol risk variable, we have a very non-normal looking variable, 50% at the lowest category of abstinence, and the categories correspond to the World Health Organization categories based on how much people drink per day. So with this, you should not treat it as a continuous variable with linear relations because of this strong floor effect of 50% being in the abstinence category. It gives biases in correlations and regressions because the usual linear regression assumptions are not fulfilled. But we can analyze it as an ordered categorical variable with 5 categories. So the floor effect is not a problem then. There's no assumption that is violated in that analysis. Interestingly, there has been a discussion in the alcohol literature whether you should use a binary or an ordinal representation of alcohol risk. Traditionally, abstinence is the accepted outcome in the treatment evaluation. So that's a binary variable, abstinent or not. But more recently, low-risk drinking is an alternative endpoint. And that's discussed in this Vitkiewicz article. Dataset 2, suicidal ideation and substance abuse. That we have the classic question of what influences what. So another cross-lagged question. Data are from a preventive intervention study. Sample size a little bit lower, 700. And we're looking at 8 time points and ages 19 to 26. And several references here giving various analyses of these data. Here we have an outcome. This is suicidal ideation. The number of occasions where you have had suicidal ideation thoughts or behaviors endorsed in the last year. And we see then that at age 19, we have 77% at 0. So that corresponds to age 19. The Y variable here, 23% have had at least one suicidal ideation thought in the last year. So 77% are at 0 and 8% at 1. So fairly few people in the non-zero categories, which means that you might just as well dichotomize this variable into 0 versus higher numbers. And we also have substance abuse and dependence criteria, and you see the prevalences here over age and being even lower for the substance abuse variable. The third data set is negative affect, and that's data from Notre Dame study of health and well-being. Sample size almost 300, and here we have 56 time points, daily measures on consecutive days. We work with 10 negative affect items on a 5-category scale: afraid, ashamed, guilty, hostile, etc. Where the question format is this 5-category scale. 1, I haven't had those feelings at all, a little bit, moderately, quite a bit, extremely. So when you work with the sum of those items, which is often the case, you get this kind of a distribution. 54% at the lowest value, So fewer at the floor effect than for the suicidal ideation. So you have more action, more information in the tail here. So 54 at the lowest value, answering not at all on all 10 items. So you would say then that that's not suitable for a continuous variable analysis with linear models because of this strong floor effect. But it can be treated as a semi-continuous variable, and that's how we're going to take a look at that variable towards the end of this talk. In section 2, I turn to a brief refresher of longitudinal modeling with continuous outcomes. And we're talking about short longitudinal data here. So on slide 14, you see 3 different kinds of so-called dynamic models, which are models that are typically used in time series analysis. So the simplest one being the autoregression model at the top here with lag 1, so y3 is influenced by y2 but not directly by y1. So you have the autoregressions and the uncorrelated residuals there. And you can also add a random intercept to that. I call the random intercept I and write it in a notation that shows that it's a latent variable, an unobserved continuous latent variable, influencing the outcomes equally at all time points. And we still have the direct influence between the y of order of lag 1, just like at the top. And you can also work with a random intercept ARMA model. So comparing the model 2 here and model 3, what we've done is we're saying that y3 is influenced by the random intercept, by y at the previous time point, and by the residual of y at the previous time point. So you have a moving average component added to the model that tends to be able to pick up correlations across a larger time point instead of adding, say, AR2, AR3, etc. So in all 3 cases here now, the way we're drawing these models is important. We're describing them as in a single level wide format, to use modeling terms. Single level wide format, and boxes are observed variables, of course, and the circle represents a latent variable. Now, looking at it from another perspective, we can go back to the standard statistical theory used in repeated measurement modeling. We have the Laird and Ware article in Biometrics, the classic article, talking about random effects that is latent variables that pick up heterogeneity among individuals. And we have the Chi and Reinsel follow-up article in JASA, Journal of the American Statistical Association, where the autoregressions among the residuals were added. So here's a first-order autoregression going on. So we can draw that in the special case of no trend, so the only random effect is the random intercept, plus these first-order autoregressions among the residuals. So what's important here now is, in contrast to the previous slide, the relationships between the observed variables is such that there's no direct regression of y3 on y2, for instance. The autoregressions is among the residuals. So the residual is what is left when the random intercept has been subtracted out from y3. So it is the effect of it's autoregressions among variables that are not influenced by the random intercept at all. And in the literature that we are going to take a look at, that it's referred to as a division between variation, between individual variation, and within the individual variation across time, much like the separation that we do in multi-level regression analysis. Once again, the figure corresponds to a single level wide format analysis, which is suitable for short longitudinal data. Now this picture can be drawn, just to repeat it here at the top, can also be drawn as shown below, where you explicitly state that these residuals are unobserved latent variables, so factors to use psychometric language, that influence each y variable, and it's the relationship between the factors that we're interested in. So that if you look at y3, for instance, this factor influences y3 with the so you can regress y3 on that factor with the residual at 0, which means it's the same thing as this y3 residual, which we write as y3 hat to play on notation used in the Mplus program. So here we have that separation of between and within individual variation clearly done in two different ways. So we call this an RIAR model, random intercept autoregressive model, which is the univariate part of random intercept cross-lag panel modeling, RICLPM, as suggested by Hammacher and others in 2015. So in the cross-lag model, you add a second process, which looks like this, and where the factors or the residuals have cross-lagged effects. Now you can go further with this and go to RI-ARMA modeling on slide 17, where you have the same idea, random intercept, and you have relationships over time that are between variables, these factors, that are not influenced by I, so you have the separation between the between and the within variation. But now you have a moving average component here as added as well. So that's innovation brought forward in this paper, residual structural equation models, and how to estimate it by maximum likelihood estimation in this case. And it's also discussed in this web talk number 4, part 1, which deals with the continuous case. Now turning then to section 3, I'm going to give you a brief introduction to multivariate modeling with categorical outcomes, specifically the multivariate probit model. So on slide 19, we can take a look at this figure at the top left, and in the previous cases, these arrows meant linear regressions between continuous variables. So what does it mean now when the observed variables are dichotomous or binary instead? Well, in the context of, say, item response theory, it would look like this. You have the ability factor, say normally distributed here on the x-axis, and the outcome is 0, 1, and you have a model for the probability that y is 1 on item j, such that it's for increasing ability, the probability of answering the item correctly increases. And items can be of different difficulties, so with an average ability, the probability of getting this item right is very low versus this item where the probability is very high, an easier item. So we talk about item difficulty, shifting the curve sidewise, and discrimination, which has to do with the steepness of the slope. Here we have a fairly lower steepness than in this curve. In factor analysis, we instead talk about item thresholds and factor loadings. But we're going to focus on the random intercept, so the factor is actually a random intercept, in which case this would be 5 different time points, again in a single level wide format. And the factor loadings are fixed at 1. The influence of the random intercept is the same at all 5 time points. Now typically in these models then, with categorical outcomes, you specify a normally distributed latent variable, and then so that's this normal distribution here, and then probit or logit regressions here. And the difference is not that large, but for reasons that will become clear, we're going to focus on probit regressions. Estimators, at least what's available in our Mplus program, is maximum likelihood, weighted least squares, and Bayes. Now on slide 20, if we go into a little bit more detail here, we can represent this model equivalently using so-called latent response variables y star, which are continuous latent variables. And this is a well-known approach to describe even probit regression. So when the y star exceeds the threshold, we have the response y equals 1, otherwise y equals 0. So you can think about the y star as a specific ability that you need to solve a specific math item, for instance. And when the ability is above a certain threshold, you get it right. Your ability may be way above or just above, but you make that you only have this dichotomous measure. So it's imagining that you could have a more fine-grained measure of y star. Now, specifying normally distributed factor together with probit regressions is the same as specifying normally distributed latent response variables y star. So you have a normal factor here and normal residuals. Then you get normal plus normal, which is a normal y star. If you have logistic regression, however, then you have logistic densities here for the residuals, and that does not give y star normality. And it's useful to work with the probit because then you have a multivariate normal vector variables that makes it possible to do all kinds of general linear models between those y stars. Now, as an aside, the correlations between the y star variables for binary y are the so-called tetrachoric correlations, and they are used in the analysis of this simple weighted least squares estimator. Whereas maximum likelihood and Bayes use raw data, so full information estimators, which is advantageous. And we're going to focus on Bayes in today's talk. Turning to slide 21 then, the cross-sectional modeling of IRT and factor analysis focus on the relationship between f and y, but what we're going to focus on is the longitudinal modeling of panel data, which adds a focus on the relationship between the y's at different time points. So we're saying here that the random intercept may not account for all the y star correlation across time, especially not when the occasions are close in time. Now, if you have a multivariate probit model, as we've mentioned, that will allow linear regressions among normally distributed y stars, just like in the below autoregressive model, so a dynamic model in time series setting. So you have the y stars here, and you have a direct relationship between them, as in the first picture that I showed you for the continuous case. And the question then, we're saying that I does not account for all the correlation. You have to have relationships between the y's or their residuals on top of that to capture all the relationships in the data. And the question then is if the autoregressions should be among the y stars or among the residuals. And we will focus on the latter in this talk. Turning to slide 22 then, here is the statistical specification of this RI-AR1 multivariate probit model with the residual autoregressions. So we're going to draw it then in terms of the random intercept and the y stars. Each y star is influencing the observed response so we have a threshold formulation in between here. So for each time point we make a distinction between y star and y in this elaborate way. We may skip the y stars after a while, just think of knowing that they are part of the model specification. So we have these regressions among the residuals, and those regressions also have their residuals. So again, the binary case is a continuous latent response variable at a certain time point exceeding a time point specific threshold tau. When it's greater than tau, you get y equals 1, otherwise y equals 0. So y star for individual I at time point t is a random intercept, which I call alpha sub I, so that's the I up here. A random intercept plus a residual, which I just call y hat star at that time point. And it's these y hat stars that have an autoregressive relationship. So here beta t is the autoregression plus a residual z. And that's for time point 2 to t. The first time point is different, and that's just a residual then coming in, essentially. So the random intercept is assumed to be normal, just like we assume normal factors with certain random intercept variance psi. The residuals are normal, uncorrelated with the alphas. zero mean and variance is theta t. Now the interesting thing here is that we can only identify a maximum of t minus 1 theta t variances, and often far fewer than that. And it becomes an empirical identification issue where the number of identifiable variances depends on the data, depends on the correlations across time, depends on the number of time points. And we usually default to specifying that the residual variances are equal and fixed at 1, perhaps freeing the first one, since it's a little bit different. Now, in terms of estimation, maximum likelihood is intractable. If you try numerical integration, it leads to too many dimensions of numerical integration because of the categorical outcome nature combined with continuous latent variables. Now, weighted least squares uses a second order limited information estimator, or tethachoric or polychoric correlations, or polyserial correlations. It's very fast, so it's a very good estimator then with low missingness. Does not handle missing at random, however, but when you don't have much missingness, it's gives results very close to full information estimators such as Bayes, which we're going to focus on here, which uses then raw data, and it's advantageous, of course, then to use a full information estimator because it handles missing at random correctly. So that's described in this RSEM paper. And you have the papers also shown in the reference list at the end. Now, then models need to be identified in terms of the second order information. So even if even though you use higher order moment information, raw data, the model has to be identified in terms of the second order information due to the multivariate probit assumptions. So talking about identification, slide 24 gives an interesting visual summary of what goes on in this RI-AR1 model. So if you look at the top left picture here, time is on the x-axis, and the y-axis is the correlation between time 1 and the following time points. So we're going to focus, for instance, on the correlation between time 1 and time t here. And we vary the autocorrelation coefficient here from 0 to 0.25, 75 rather. And we see that the correlation across time goes down towards 0 after a few time points. If you take an average autoregressive coefficient here of 0.5, it goes down towards 0 around 7 time points, and for lower regression coefficients already at 5, whereas for 0.75, very high AR, it doesn't go down to 0 quite here. Now that's for RI variance of 0, RI variance of 0.25, then you have a lower asymptote of 0.25, and that is correlations do not go down towards 0 across time. And then you have 0.50 here, you have a higher low asymptote, and 0.75 here. In fact, if you look at the formula for the correlation between y1 and a later time point t, it corresponds to a sum of the random intercept variance, and this is on a standardized metric, so it's the r square, plus the autoregressive coefficient to the power of t minus 1 times 1 minus psi. So this second term here, for a big difference, say t equals 10, beta is a value less than 1, so beta to the power of 9, say, would be a very small ignorable value. So for a large time difference, the correlation goes down to the residual intercept, the random intercept variance psi. And that's what we see, say, top right here. Goes down towards 0.25, which is the r square in that case. So this is a way then to see that with long time distances, second term is 0, so correlations identify the random intercept variance. And once you know that, then for sure all other correlations, you can deduce what the autoregressive coefficient is. So that's one intuitive way of seeing that you have identification in that sense. Now, in practice then, how does this work out in simulations? AR1 with binary outcome. So this is working with time-varying thresholds, so we do not impose any structure on the levels or the probabilities across time. And we also let the autoregressive coefficients vary across time in the estimation. No missing data here for simplicity, so we use the WSMV estimator because it's fast, but the base results will be similar than due to no missing data. Parameter values, autocorrelation 0.3, fairly typical value. And the R squared due to the random intercept around 0.5. And fairly low prevalence here to match the suicidal data that I mentioned in the introduction. So fixed variances for these theta t's that we talked about. 3 time points, you get good result for n equals 500. But you need 500. You shouldn't go really below that. And same for t equals 4 and t equals 8. So there's no improvement to by having more time points because we do not impose any time invariance of the parameters. So now if you try to free the first variance, theta t, which is a little bit different than the others, that model is not identified with 3 time points. With 4 time points you get good results, but you need 2,000 observations. For 8 time points you get good results for only 500. Because you have more correlations to nail down the first variance, the first free variance. So having many time points makes it possible to have a smaller sample. Now if you have free t-1 variances, which in practice is often not a stable model, in fact I don't think I've seen it in these data, I have not seen it be able to converge. T equals 4 is not identified, t equals 5 gets good results, but you have to go up to 5,000 observations. T equals 8, once again, gets good results for n equals 500, but that's in theory, so to speak, although in practice in the simulation, I have not seen it in real data. Turning then to slide 26 for a couple of more slides of theory here before we get into applications. We should be mindful of the fact that there are 2 kinds of model assessments for categorical outcomes. Very often then at least in applications of the Mplus software, we look at the fit to correlations among a set of continuous response variables y star, and by a technique that was described by me and others in 1997. You can click on this URL to get to this report, which I never followed through to publication, but it's been influential anyway and useful. That's one way, looking at how the correlations are fit. But that doesn't say the model will fit the data. You also have to look at the fit in terms of the response patterns, that is the frequency table for all variables. So a model may in fact, and we'll see this, fit well to the y star correlations, but not the frequency table. So even a just identified y star model, just identified in terms of the correlations, may not fit the frequency table in some cases, and we'll see examples of that. And I discussed that in a book chapter in 1993, but I think it's been largely ignored. Now, looking at the fit to the y stars then, correlations, we have the WSMV chi-square, which works well when the number of variables is not large and the sample size is not small. So it's very suitable for cross-leg panel modeling with short longitudinal data. And you can also use the base PPP. That is using any fit statistics to compute the fit statistic for the observed data and generate the fit statistic based on the estimated model and find the proportion of cases where these differ. So that's posterior predicted p-values, posterior predicted p-value. For categorical variables, it's based on the chi-square test of the overall model fit for y stars. So it's the chi-square test. So it's analogous to WSMV chi-square, I've estimated versus sample tetrachorics and polychorics, but it has rather, unfortunately, low power for binary outcomes, and is therefore, it's less powerful than the W7V chi-square. And we have a reference to that. It is, however, more powerful for polynomous variables, so it is of use. Now turning to the other side of the coin, fit to the data in terms of frequency tables. With categorical latent class indicators, sorry, not latent class indicators, but latent factor indicators, the model can be tested against data using Pearson and likelihood ratio chi-square frequency table tests by the well-known cases of Pearson and likelihood ratio frequency table tests. But typically there are too many frequency table cells, with many cells having low frequencies, and they disagree and are useless. Even with only 8 binary variables, you have 256 possible response patterns, and many patterns are probably not observed, so you get 0 cells, and test disagree strongly. Neither one probably follow the assumption of a chi-square distribution. So alternatively, we provide fit for univariate and bivariate tables, so collapsing the data into, so you get higher frequencies, and we also look at the most common response patterns. So with that, we're ready to take a look at some applications. Turning to section 4, we're going to take a look at 2 applications of binary RI-AR modeling. First, the binary suicidal ideation example. So we have dichotomized the suicidal ideation thoughts or behaviors. So we have 8 binary variables for the 8 time points, and we're using Bayes, and the sample size is 737. We're going to take a look at various fit measures. First, the Bayes posterior predicted p-value, but then also the number of significant residuals, both for the 20 most frequent response patterns and for the bivariate cells. So 20 most frequent response patterns, the most frequent pattern is 155 observed for those who have zeros throughout all 8 time points, so none of these thoughts or behaviors. 155 is about 22% of the sample. In terms of the bivariate cells, we have 2x2 tables, the bivariate tables, and we have 28 of them, so that's 112 bivariate cells. And let's say we accept 5% of them to be significant, then even if the model is true, then that would be 6. So we accept 6 or fewer. So then let's take a look at the models. We have 6 models here. First of all, the unrestricted multivariate probit model, 36 parameters, and a PPP of close to 0.5, which is what you obtain for perfectly fitting models. And that's perfectly fitting also in terms of the response pattern and the bivariates. So this is a very well-fitting model. Of course, we are not that interested in the unrestricted model. We want more parsimonious models, but we want at least that one to fit the data, which is not always the case. So that's a good starting point. If we use a model with AR1, lag1, autoregressives, we have 15 parameters and a decent PPP. However, we have 2 significant residuals among the response patterns, one of them being the most frequent one, 155. So that's not a great outcome. And we have 22 cells that are significant, which is far more than the 6 that we were finding acceptable. So that's a poor fitting model. You can go to AR2, so add a lag2 part to the model. More parameters, PPP improves, the response pattern fit improves greatly, and the bivariates fit very well also. Question is though, do we need 21 parameters? If you go to model 4, when you have a random intercept only, you have 9 parameters, very parsimonious, and a half decent PPP, And at least we don't have the most frequent pattern misfitting, but we do have 2 misfitting. And we have 8 bivariates, which is a little bit more than the 6 that we stipulated. So that's a marginal fit, I would say. Adding an AR1 to that model, however, and these are unequal AR1s over time. So with 8 time points, you have 7 more parameters here. You get a very well-fitting model, also in terms of significant residuals and bivariates. So good fit. And then AR2 fits even better, but maybe not necessary to go up to 22 parameters. So if you look at this, it has some interesting features. If you compare model 2 versus model 5, AR1 versus RI AR1, you add just a single parameter 16 versus 25 versus 15 rather, and the PPP goes up nicely, and the misfit goes down nicely, and also in terms of the bivariates, 22 to 1. So that shows the importance of the random intercept addition. If you look at model 4 versus model 5, you see the importance of the autoregressive. So you add 7 parameters, and the PPP improves nicely, and you have good fit in terms of the significant residuals. And you don't really need AR2. Fits slightly better, but you don't really need that. So that shows the importance of having both random intercept and autoregressive features in the model. And note here that maximum likelihood can only estimate model 4, the random intercept model, cannot handle the autoregressive coefficients. WSMV can estimate all 6 models. Here are the estimates. So we look at the model 5 over here, RI-AR1, we find that the random intercept variance is substantial relative to its standard error, which is the standard deviation of the posterior distribution in the Bayes analysis. So if you look at the relationship between them, it's a significant, substantial rather, variance. And then you want to look at the standardized estimates here for categorical variables, because other metrics are not perhaps as meaningful. So you see then how the intercept is measured by the 8 indicators, the 8 Y star variables. And here are the standardized coefficients. They hover around 0.6. So for instance, if you look at the 4th time point, you can say that the R square for Y4 star that is due to the random intercept is the square of that, so about 0.4. So a fairly substantial R square. And you can then think back to the correlation plots that we showed. And that relates also to the correlation between the first and the last time point due to RI, which is the product of the standardized coefficients out here. And that's 0.38, so also close to 0.4. So the correlation even at that distance is substantial. But that's because of the RI, because the total estimated correlation is only slightly higher than that. That is the correlation that comes from the autoregressives. So one can say basically that there's no contribution by the autoregressive coefficients to the correlation over that long of a time span. It's only due to the random intercept, which is a way of saying that the random intercept variance is identified. Now, if you look at the autoregressive coefficients, standardized, in Mplus we have the hat notation for the residuals. So time point 2 on time point 1, insignificant. Time point 3 on time point 2, insignificant. But then when we come to time point 4 on 3, we start to see significance here, and for the remaining time points as well, which shows the value of allowing the autoregressive coefficients to be different across time, which you can do easily in the single level wide format analysis that we're doing. So if you restricted the autoregressives to be the same across time, the average, the value that you would get would be attenuated by these 0 or even negative coefficients here at the beginning. Turning then to the second example, binary abstinence, that is dichotomizing the 5-category abstinence variable. So here we're working with 1375 people and still 8 time points, week number 1 through 16. And again, we look at the base PPP and the number of significant residuals. And here the most frequent pattern is again all zeros, 312. And 6 is still the threshold for an acceptable model. So the unrestricted model then, once again, 36 parameters, good PPP, but also good fit in terms of significant residuals. We have one response pattern that with observed frequency 38, that's significant. It's a z-score of 1.98, so just barely significant. So I would say that the unrestricted model fits well even here for this example. So it's worth trying to find more parsimonious models that are nested within that unrestricted model. AR1 doesn't fit too well. High number of significant residuals, and also does not capture the most frequent pattern. AR2 does a lot better. Then if you go to RI only, it doesn't fit well in any of the three, by any of the 3 measures. If you add AR1, those 7 parameters, however, you get an okay fit. And if you go to AR2, you get a good fit. So once again, going from AR1 to RI AR1, adding 1 parameter, improved things quite a lot in all regards. And going from RI, which shows the importance of RI, and going from RI to RI AR1 also improves fit, which shows the importance of the AR1 parameters. Turning then to section 5, we go from binary variables to polynomous variables, ordered categorical or ordinal outcomes, and we're also introducing 2-part ordinal modeling. So slide 34 then goes back to the histogram that we looked at for the 5-category alcohol risk outcome, which has a high percentage in the abstinence category and then leveling off over the higher categories. And what you have plotted here at the bottom is the proportion drinking, that is the non-abstinent people, starting with week 0 before the treatment started and through then the 16 treatment weeks. So at week 0, before the treatment started, the proportion was 1. So all of the people were drinking. So this was a treatment for drinkers. And then after the first week of treatment, it dropped down to 0.45. So 45% were drinking. So that's a pretty successful treatment then, as judged by the first week. Proportion drinking dropping from 1 to 0.45. And then, however, in week 2 it goes up a little bit. So after week 2 it sort of stabilizes at the level of half of the people having a successful outcome of abstinence. Now, if you look at this a little bit more in detail, I'm now plotting from week number 1. I'm dropping week number 0 here. And so the first curve is just the same as what we had on the previous slide, starting here, goes up and stabilizes. So this is now looking at the 5-category variables. So that curve is for categories 2 plus 3 plus 4 plus 5. And down here we have category, the highest category, the sum of the highest, 2 highest, and the sum of the 3 highest. When we look at this, we see then that looks like these bottom 3 curves are fairly parallel but the top curve is not showing the same shape over time as they are. You can actually then so you can question whether or not the standard ordered categorical, logistic, or probit model is appropriate here. It has this proportionality assumption. And you can actually do this test called the Brandt test, chi-square test of this proportionality, where you essentially cut the variables at these different cut points and indicated by these curves, and then test if the slopes are the same. And here it is in the regression against time, against week. And we reject proportionality here. So proportionality seems to hold, however, for the 4 highest categories, which suggests a 2-part model, 1 binary part and 1 4-category ordinal part. So this test, although we're not doing an analysis against time, we're not using a growth model, it is still a useful test as an indication that maybe all is not right about the proportionality assumption, and maybe we should go to another model. Which is interesting then, just by going back to what I talked about in the beginning. In the treatment studies, traditional abstinence was the only accepted outcome, so a binary outcome. But more recently, low-risk drinking is an alternative endpoint. Wouldn't it be nice if we had a model that looked at both of them at the same time? And that is what 2-part modeling does. Here we have it described for continuous outcomes. So you have an original variable here, and what you do, and you consider, say, a growth model. So here you have a random intercept and random slope. What you do is divide the variable into 2 parts, 1 binary part and 1 part that represent distribution above the lowest floor point. So the variable is split into 2 parts. When y is greater than 0, you have a binary indicator that's 1 versus 0 if it's at 0, if y is at 0. And then you create not only u but also a variable v, so that when u equals 1, you take the log of y to pull in the tail and make a normality assumption more palatable. And if y is 0 so that u is 0, then you specify v as missing 999. And if the original variable is missing, then both of those are missing. So that's essentially what was done in that 2-part growth modeling article by Wilson and Joe Schaefer in 2001 in JASA. And it really goes back to work by Naya Duan in 1983, 2-part regression for medical care demand in Journal of Business and Economic Statistics. And I also took a look at this in the context of growth mixture modeling, looking at 2-part growth mixture models for cases where you had a high piling up at 0. Now, for ordinal outcomes as opposed to continuous outcomes, we actually looked at that in our book, Regression and Mediation Analysis from 2016, where we suggested that you could do a 2-part regression analysis with an ordinal outcome as well. You would not do the log y transformation, obviously, but still. And this was also discussed in my web talk here, number 4, part 2, cross-lag modeling of categorical panel data, which is a longer version of the beginning of this talk. It's 5 hours actually. And in Mplus version 8.8, the latest version, we have improved the testing output to get that correct for 2-part ordinal multivariate probit in the so-called Tech 10 area section. I actually emailed with Don Hedeker about this because I thought maybe he would know about work in this area, and it seemed like nothing has been written. I may be wrong, and you may know more than I do. But he said he had worked with a student on this in the longitudinal setting, but it didn't come to a paper. So go on to slide 39 then. we can take a little time here, since this is an ASA talk, to look at the formulas for the univariate regression case in two-part modeling, and I'm still in the continuous case now. So with censoring from below at 0 and using probit regression and having u equals 1 referring to a positive outcome instead of 0, the two-part model can be expressed by a probit regression part, this one, and a continuous regression part, equation 5. So in equation 4, the probability u equals 1 as opposed to 0 is then described here by the phi function. That is a standard normal distribution function with threshold tau, that is negative tau intercept, and slope gamma 1 times covariate x divided by square root of sigma square, where in this case the variance is 1, which we usually have, as we usually do in probit regression. Later on it won't be 1. And then the other variable is now the positive variable, so to speak, is log of y for those who have u equals 1. So that's a linear regression with a normal error. So once we've taken the log, we can assume normality for the epsilon. And the important and useful thing here is that gamma 1 and beta 1 can be different. We can even have different x's. So the influence on the two parts of the model can be different. And logit can be used instead of probit in equation 4. Alternative models then are an inflation model using a mixture with a zero latent class, which may give very similar results. The question is if you want to conceptualize it that way. In the drinking case, one wouldn't really think about a class of non-drinkers. Everybody drinks. It's more of a two-step procedure in how the data are generated. First, the individual decides on whether or not he or she will drink, and then more or less consciously how much they will drink. So the two-step flavor of the model is useful, although I think it's useful in any case where you have a large portion of the data at 0, and they've got to be you're interested in formulating a model that gives a chance for a different process being related to the zeros as opposed to the non-zeros. Heckman selection modeling is also an alternative, and censored modeling, censored normal, Tobit modeling, using Art Goldberger's term. Censored inflated is also an alternative that we will not consider. So now, reminding us then on slide 40 about the regular ordinal regression case, and then we'll take a look at the two-part ordinal. You have a y-star distribution that is normal, and you have these different thresholds. So with 5 categories, we have y equals 0 through 4, 5 categories. So we have 4 thresholds tau. And in regular ordinal probit regression, and it's similar to ordinal logit regression, categories goes from c equals 0 up to c minus 1 then to get c categories. Probability that you are in a certain category is the difference between the areas under the curve. So the area from here under this tau, minus the area under this tau would be the probability of falling here. So you subtract the mean, which could be a function then of x. Now in two-part ordinal with the same categories, you use the probit regression for the event u equals 1, referring to a positive outcome. So that's u equals 1. So you have this standard binary probit, and then you have a ordinal probit model for the higher categories above the floor. So you have this difference here for the for the positive part, so to speak. So you divide it up, and the parameters in the binary part are different from the parameters in the positive part. So, and in the multivariate response case, you're not looking at just one time point, but 8 time points, for instance. The variance is sigma square and sigma square p contain key model parameters like the random intercept variance and autoregressive coefficients. we're going to apply this then on slide 41 to the 5-category alcohol risk outcome of the combined study, looking at the treatment weeks 1 through 16, t equals 8. And we are going to be interested only in a random intercept model. We're not going to put any mean structure on here and not consider any random slope. So it's only these two random intercept. We're going to compare the regular and the two-part ordinal analysis. First, we're going to model only the alcohol risk outcome by itself. And then we're going to model the effect of treatment on the alcohol risk outcome. So we're going to have a treatment variable here, actually 8 dummy variables corresponding to the 9 different treatments. And we're going to be interested in possibly different effects on the binary part as opposed to the ordinal part. So looking first then at the alcohol risk outcome per se, and we're testing it for the t equals 8 for the 5-category alcohol risk outcome, and most frequent pattern again is 312. And now we have bivariate tables that are 5 by 5, and that gives you a total of 700 cells. So the 5% threshold there is 35 in this case. So slide 43 then gives you a series of models, and then model fit results for regular ordinal regression and two-part ordinal regression. First model that we look at is for the estimator maximum likelihood. In the probit case, logit is similar, where you have a random intercept. We can only do the random intercept model there. No other regressive coefficients. And we see then that that is misfitting. We have 11 significant residuals for the 20 most common response patterns, including the most frequent one. Not a good look. And the bivariate tables, 41% are bivariate cells, rather, 41% are misfitting. Then we go to base, where we have the luxury of being able to look at an unrestricted model. And we see then that although the PPP is good, we have a good fit to the Y-star correlations. We have a fairly bad fit for the response patterns, and also very bad fit for the bivariate cells. So here's a case where, yeah, you get a good fit to the Y-stars, but you don't get a good fit to the Ys. So you should give up on this model. There are more parsimonious models, but they will also, of course, be poorly fitting, since the most unrestricted version of them was poorly fitting. So we have to go to two-part ordinal. So you have then the maximum likelihood model here, and it has 2 more parameters than the regular ordinal. What are those parameters? Well, you have 1 more random intercept. You will have 1 both for the binary part and for the ordinal part, and then you have the covariance between them, so 2 more parameters. And you see the log likelihood gets much better for only those 2 parameters added, and therefore the BIC gets much lower, much better. And the fit, of course, is much better, but still not good. We have too many misfitting residuals here. Now if you turn to base then and look at the unrestricted model, PPP is good, and in this case we actually have good residual fit, both for the response patterns and for the bivariate cells. So then we can investigate more parsimonious models like the random intercept model, which does not fit well. Bad PPP, not great response pattern fit, and not great fit to the bivariate cells. Adding AR1, so adding in this case 14 parameters, 7 AR autoregressives for each of the 2 processes. That's 14, that's 45, 49, yes, right. That gives you a better PPP and a decent response pattern fit, and we're getting down to 9%, so close to the 5% that we find can be acceptable. And adding AR2 you get an even better fit. But you could stay at base RI-AR1. So once again, showing the importance here of base being able to investigate more features, and both RI and AR being important. So now we take a look at the treatment effects. So we're regressing on the 8 dummy treatment variables, with the placebo being the reference group. So we compare regular versus 2-part ordinal RI-AR1 models. And looking at the treatments here, and here's the regular model, and here's the 2-part model. So they agree, the two approaches, the two models agree that treatment number 2 is not successful, non-significant effect. And this is the effect on the random intercept, obviously. Then treatment number 3, significant for the regular model, but for the 2-part model, it's only significant for the binary part, not the ordinal part. Treatments number 4 and 5 are significant for the regular approach, but we get more detail here for in the 2-part approach. Both the binary and the ordinal parts are significant, which could be of some substantive interest, that those treatments, and they are the only treatments that have effect on both parts, both on the decision to drink, or drinking or not, and also on the amount of alcohol that's being consumed. And here they disagree, the two approaches. For treatment 6, regular approach significant, 2-part non-significant. Treatment number 7, 2-part says it's only significant for the ordinal part, that is how much you drink, and for 8, significant only for the binary part. And they both agree on treatment number 9. So that's sort of interesting how you get different results, and perhaps more detailed and interesting results when you switch to the better fitting 2-part model. In section 6, we then turn to the analysis of 2 processes. So doing the cross-lagged panel modeling. And here it is on slide 46. We're showing the example of the standard RI-CLPM, that is what I could also call RI-AR11, so autoregressive order 1, lag 1 for each of the 2 processes. So we're showing it here, one process at the top, one at the bottom, and it's the residuals that have the cross-lagged relationship across time. And the 2 random intercepts are correlated. We could also have drawn it with circles representing factors that are the same as these residuals. So there would be 2 rows of factors that have cross-lagged effects. Same thing. Now, this model was developed for continuous outcomes in this paper in Psychological Methods, 2015. The case of categorical outcomes has not gotten a full treatment until recently. In the paper by Asparahov and myself, Residual SEM, that's going to be published in the SEM, Structural Equation Modeling Journal, and also in the accompanying web talk that I recorded, web talk 4, part 2 now, where part 1 was the continuous outcome case. We're going to take as an example the bivariate analysis of stress and alcohol risk. So this is again the treatment weeks of 1 through 16, 1,375 individuals and 8 time points. And we return then to the question in the introduction: does stress influence alcohol risk, or is it the other way around? And again, this paper by Armely suggested that stress causes drinking, not the other way around. But the alcohol treatment setting may produce a different picture. We're going to use an RI-CLPM with 1 continuous and 1 categorical, 1 ordered categorical outcome. So bivariate analysis, and first I'm taking a look at the average correlations for each of those two processes as a function of the time distance. So this corresponds to the correlation plots for RI-AR components that I showed you earlier, the artificial ones, where we have the same time distance in weeks here on the x-axis, and on the y-axis we have average correlation. And the correlations go down. It starts quite high for alcohol risk, and a little bit lower for the alcohol risk is the binary part, and a little bit lower for the stress part, but both of them end up fairly high even after at the last time point here. So the correlation between the first and the last time point is higher than 0.5. So we would expect then a random intercept variance that is substantial, and we would be able to that should be able to fit the data well with that when we include an AR1 process on top of it. And this model for the stress outcome was one of the models considered in the Sparrow-Mutien paper. Now for the ordinal alcohol risk variable, the RI-AR1 model is also chosen. So that's for the 5-category alcohol risk variable, which we are going to analyze, whereas the plot only shows the correlation for the binary part. So the 2-part ordinal model then has, together with the stress variable, it gives 3 correlated random intercepts, 1 for stress and 2 for alcohol risk. So we have 3 processes going on with cross-lagged effects for all 3 processes. So actually no longer only a bivariate outcome analysis. And here are the results. The number of significant cross-lagged effects out of the 7 possible for stress regressed on the binary part of alcohol risk. Only 1 significant effect. Stress regressed on the ordinal part of alcohol risk, 6, so almost all of the 7. And the binary part of alcohol risk regressed on stress, 0. And the ordinal part, 3 small effects. So in summary then, we find that most of the cross-lagged effect is alcohol risk causing increased stress, not the other way around. So it's this one that's the most important one. Regressed on binary part of alcohol risk is, in this one, regressed on ordinal part of alcohol risk. The effect of alcohol risk on stress, in other words. So it's increasing the stress level. Stress not increasing the alcohol level. Abstinence or not has little effect on stress. It's a higher degree of alcohol risk. Non-abstinence has a significant effect on stress. Stress has a minor effect on higher degree of alcohol risk. So that's looking at these 3 significant but small effects. And further topics on the categorical modeling of cross-lag panel data is given in Web Talk 4, where I discuss some other models like having the observed y variable, the categorical y, say a binary y, being a predictor of later events rather than the latent y star, still in the multivariate probit setting, however. Also looking at reciprocal interaction, so interactions, contemporaneous influence between the 2 processes. And furthermore, looking at bivariate latent transition analysis, so 2 processes going forward with a latent transition model, including mover-stayer versions of that and the random intercept LTA versions of that. All right then we're turning to the last section of this talk, part 2, with the focus on long longitudinal data, also called intensive longitudinal data, so many time points and time points that are close in time. We're going to take a look at two-level time series analysis. DSEM, or dynamic structural equation modeling, is the general framework within which we do this two-level time series analysis. Slide 52, the frequent observations, which can range up into the thousands in some cases, can come from daily diary data, like the negative affect data we looked at before, 56 days, or ecological momentary assessments or experience sampling methods, or coming from wearables. And here it's a two-level setting. Within level is time, so variation across time, and between level is individual, variation across individuals. And variation in within level parameters across individuals. So you have parameters on level 1 that are random. They can be characterized now by many random effects, not only the random intercepts. So you have the means or intercepts referring to the level, but you can also have random variances, random autocorrelations, random slopes, random amplitude in the fluctuations over time. And when you have that many random effects, you need Bayesian estimation. That's the only way that is made possible. And this was implemented in Mplus, as presented in this paper, Dynamic Structural Equation Modeling, by Asparov, Hammaker, and myself, and some other papers following that, dealing with the latent variable centering for predictors and mediators in time series models, and also this article, Comparison Models for the Analysis of Intensive Longitudinal Data. And you can find many more references and also short course videos and handouts on at this URL if you click on it. Turning then to slide 53, here is one way of representing such two-level time series data in the form of VAR modeling, vector autoregressive modeling. So in this case, the vector consists of two variables. It's going to be positive affect and negative affect. And to familiarize yourself with this, we do a between-within decomposition. So we have the observed positive affect and negative affect variables, and we have a random intercept that we pull out from that. It's called, this is from an article by Ellen Hammaker, pulling out a random intercept or random mean here, so that the remainder is then a within variable. So superscript W here for both. And the picture is then for within and for between. So the within is a variation across time, here represented by only two time points, t minus 1 and t, for positive affect, and same for negative affect. Of course, this time series continues very long series, but we only draw it for the two adjacent time points like this. So as it says here in the second bullet, these within variables are the residuals in the earlier figures, those hat variables that we used in the Mplus notation. So it's the same thing in that regard. It's influence, cross-legged influence between residuals. And here you have filled circles representing potentially random effects, random autoregressive effect, and random cross-loadings. And there are many other random effects that you may be interested in. And those random effects are latent variables on the between level, and they are correlated, and they could possibly have observed between level variables, both predictors and outcomes. So you can, in a general DSEM framework, you can have any structural equation model for these between level variables. But it is a random intercept model with autoregressive features and possibly some more random effects than just the random intercepts. So looking then at some examples, here's an example of studies of mood. And this study was designed to detect depression in adolescents. It's in the frontiers in psychology. So you have these experience sampling method questionnaires measuring positive and negative affect in Dutch adolescents, 12 to 16. Sample of 233, several measures per day for 7 days. I think it's about 8 measures per day for 7 days. And if you look at that model, and I'm taking a very modest approach to it, just staying with random intercepts only in this case. And I'm going to take a look at the relationships on the within level, that is the cross-level effects. So for instance, PA on PA ampersand 1 refers to the lag 1 autoregression of PA at time point t on PA t minus 1. So because it appears on the within level, it's a residual of PA, that is the latent variable centered version of PA. What's left in PA after the random intercept has been subtracted. So then you have this autocorrelation PA on PA at 1, and then what we're interested in, PA on NA at the previous time point. The estimate is very small and insignificant. The 95% interval, credibility interval, covers 0, so it's not significant if you use ML terms. And then you have the autocorrelation for the negative affect is strong positive and significant, but the cross-lagged is not significant. And that's often found in studies of positive and negative affects, small or insignificant cross-lagged effects. And that's certainly the case here as well. And I think it was the case also in Hammacher's study in the reference that I mentioned before. Now, reminding ourselves, however, of what we talked about in the introduction, negative effect distributions are often looking like this. Here in these data we have as high as 60% at the floor here, at the lowest value. And could that be a possible reason for the small cross-lagged effects that we saw? You know, when we have a variable that's censored this much, that causes all kinds of distortions in regular linear models. So what about a two-part model? Seems like it's motivated, and it can be done in DSEM. So you have a binary part, which uses a multivariate probit, and a positive part, in this case, then considering this tail as continuous, specified as continuous normal after we have done a log transformation. So log normal error. Now if you do that, so this shows that DSEM can be done for categorical outcomes as well as continuous ones, and the combination of them. Then just the notation here, NU refers to negative affect for the binary U variable, the binary variable U, binary part of negative affect being greater than the floor, and POS refers to the continuous part where we use linear regression. So once again, if you look at the cross-lagged effects, you have PA on U at 1, ampersand 1 rather, negative and now bigger and significant. The credibility interval does not cover 0. And likewise, we have a significant effect, albeit smaller, for nu on PA. So this says that if you are above the floor of negative affect at a previous time point, so you have a certain amount of negative affect, or feeling a certain amount of negative affect, you have a lower positive affect at the next time point. And then you have a reverse effect, but it is only half the size. So that's bringing in two-part into the two-level modeling for intensive longitudinal data. On slide 58, I turn to the topic of cycles. So here you have, for the same data set, daily cycles of positive affect. So it's observed averages over individuals from Tuesday through Monday. So you see this cyclic behavior. The positive affect goes down in the early part of the day and then up, down and up, down and up, down and up throughout. And the question is, can we account for this? Can we model this? And that then goes back to techniques for modeling cycles. And there are many ways to do it. And we're going to focus on a sine-cosine approach. So you have these cycles, for instance, 24-hour cycles, circadian rhythm, such as heart rate, going like this. Behavioral cycles, like weekly drinking pattern. Environmental cycles, like monthly temperature fluctuations. We can attack that by a sine-cosine approach, where you have essentially a linear regression here. Beta 1 times x1 plus beta 2 times x2. It's just that beta 1 is a function of two parameters, amplitude and phase, and so is beta 2. And the x1 is a sinus function of 2 times pi, that's the 3.14 pi, and a frequency index times t, time. And the amplitude, the fluctuations up and down, for instance, is then a nonlinear function of those regression coefficients. So is phase. And again, W is a frequency index with 8 measurements per day. A daily cycle is obtained as 1 divided by 8. And now you could be interested in random effects, individual variation in amplitude and phase. And that can actually be done in Mplus via random effects for beta 1 and beta 2. And I'll describe that more in a forthcoming web talk. And this approach is used in the literature. It's called a cosinor model, and a two-component version of it. So it's several more than one peak or valley within the cycle was applied by Madden and others in statistics and medicine with 4 random slopes with the application of blood pressure. Now, I use that for the daily cycles, just a one-component version. And it seems to fit the averages quite well, with the exception of the weekends where people are unexpectedly happy, at least unexpected by the model. So you may want to add dummy variables for weekdays, or for at least for the weekend here, to make it fit better. So the estimated model uses a 2-level dynamic structural equation model, allowing for these individual cycles using the sine-cosine function. And that's a paper in preparation. Now, you can also look at more than one variable across time. Here are daily cycles of positive affect and feeling tired. So you may, and they seem to have opposite cycles. When you're happy, you're not. When you're not tired, you're happy, and vice versa. But you may want to ask the more interesting question: are the two outcomes related after we account for the daily cycles? So after you've taken out these cycles, is the residual, or the residuals between the two processes related to each other? It's like having a growth model, and you're asking, after you take out the trend, is there any interesting effect left? So that's what we call residual dynamic SEM, or RDSEM, also described in this paper from 2018 and in subsequent papers. Finally then, here's an interesting application, a randomized trial in the intensive longitudinal setting in Journal of Consulting and Clinical Psychology. Interesting design here. I've applied to 119 people. So you have a baseline intensive data collection period, 6 days, and with 10 measurements per day via digital wristwatch. And then you have a randomization taking place into 8 weeks of treatment or control. And then you have a post-treatment post-treatment phase, where you measure ESM again in 6 days. So another 60 observations or time points. So the total number of time points is 60 before treatment and 60 after. And positive affect here then for some of the pre-intervention measures also shows cycles. Now, then that creates a possibility to look at interesting treatment effects. So at the bottom here we have a negative or positive affect rather before the treatment, shown here by 2 time points, pre and then after treatment. And they're characterized by a random autoregression in both places and a random intercept, a random residual variance as well in this case. So you can look at the treatment, if you can then characterize the pre-treatment period by random effects, in this case 3 latent variables, 3 random effects on the between level before treatment, and see how they relate to the random effects after treatment. So they have an effect, they relate to each other of course, and the treatment influences the post-treatment random effects. Treatment is a between level variable, person. So treatment influences the random effect, but also influences the effect of the pre-treatment random effect. So it's an interaction between TX and the pre-treatment random effect in their influence on the post-treatment random effect. So very interesting treatment effects that you can tease out with this pre and post design. So intensive measurements, not just one baseline measure, but in this case 60 time points before treatment. So preliminary findings here for this intervention study were that there was a positive effect on level on the intercept post-treatment, higher effect on level for persons with higher pre-intervention level, and also a positive effect on level, post-treatment level, for persons with high pre-intervention autocorrelation. So that may be of interest then substantively for the experts in that field. So then we finish with just the references here. Further DSEM references, simulation study to see how many people and time points you need in these analyses. There's a introduction to dynamic structural equation modeling written by somebody else, McNeish, and another application paper by Hamaker and others, which is an interesting take on it, starting with time series modeling of each person, so n=1 analyses, building up to 2-level analysis, which is forthcoming as a chapter in this handbook. And then Dan McNeish has been active again here with measurement modeling, that is more factor analytic aspects of DSEM, showing how that can be handled in this same Mplus DSEM framework. And again, more references in the short course videos are given here. And a forthcoming Web Talk 5 will focus on this long longitudinal modeling using Mplus with the inputs and interpretations of the outputs.